Dr. Narasimha MS, working in the Department of Information Science and Engineering. I am an assistant professor. Today I will be dealing the topic called K-maps. Okay. So this K-map comes in the course called Analog and Digital Electronics for third semester students. Okay. As part of the university curriculum, we have this particular course in third semester as a very core subject. Okay. So before getting into the K-maps, let us understand why this particular K-map is required, or what was the things which were present before K-maps and why these K-maps are very much required. As all of you know that today all the digital circuits are designed with logic gates. So logic gates are the very core component or core element or the fundamental elements to design any digital electronic circuit. When I start designing a circuit for the given problem, I need to understand the problem, I need to analyze the problem, and I need to do the design part of the problem. So before I go for the exact development of the problem should be understood very well, and if it is possible to simplify the given problem, then I should simplify it, then I should proceed for the design. In this context, K-map is one simplification technique which is used in digital electronics to simplify the given Boolean algebra expression or the given Boolean function. Now, what is Boolean function? Boolean function is a function having the variables present. Let me put like this. A variable I can also call in digital electronics as a literal. This may be present in an expression either in its normal form or complement form. What is normal form? A value present for a particular literal is 1, we call logic 1. Then I call that particular value as a normal value and the variable is a normal variable. Then what is a complement variable? A complement variable will going to get the complement value, means the true value is 1, always the complement value of a true value is 0. So that means every literal is presented, or it will be present in a given Boolean expression either in its normal form or complement form. After having said this, the next thing we need to understand, because all these things are prerequisites before understanding or learning the K-map. Okay. Now, there are two types of logical expressions. What are the two different types of logical expressions? We have sum of product expression and product of sum expression. Sum of product expressions are the expressions which are having a term with dot operator. I mean to say that, for example, if I take a literal like A, B, A bar, B bar, or A complement, B complement, I mean to put it, I mean to say in a very proper way, A dot, A bar dot B bar. The dot is a multiplication operation. All of you know that multiplication operation is obtained in digital electronics using AND logic gate. So always logic gate plays a major role in designing a digital electronics circuitry or digital circuitry. So A bar dot B bar is a product term, and I call that as, if I add like that so many terms, I call that as sum of product terms. I will be going through that in my forthcoming slides. Next, I have A bar plus B bar. I call that is product of sum form. If I say that A bar plus B bar with a parenthesis into B bar plus C bar, I call them as product of sum form, because two terms are having a plus, then I call that as the product of sum form. So we have two forms basically, SOP and POS, we call in short notations. So these type of functions will be given to you and you need to simplify. Okay. Let us understand why simplification is required, or before K-map what were the methods which were present to simplify, or what are the methods which are simplify even today? See, all of you know that we have Boolean algebra laws. So, one such law I may tell De Morgan's laws we have. De Morgan's law for addition, De Morgan's law for multiplication. Now, along with that we have so many laws, say for example distributive law, associative law, commutative law, like that there are so many laws are there. I can use these laws in my simplification process and I can simplify the Boolean expression which is given to you. Why the Boolean expression is given to you? The Boolean expression will going to represent one logic circuit actually. That logic circuit should be designed, but before I design that I simplify and design. Always when I simplify and design something, the number of gates required will be very less. If I do not simplify, if I straight away go for the designing a logical circuit for the given expression, then which consumes more number of logic gates. When more number of logic gates are consumed for a given problem statement, then the circuit, overall circuit will going to consume much power, or so much of power is consumed. When so much of power is consumed, when so much of power is dissipated, so the logical circuit may not last for long time. So that is why we always have to have a circuitry which consumes very less power, as well as when we have less number of gates, my design cost also get reduced. If I use more number of logic gates, definitely it will going to shoot up the overall cost of a design. So in order to overcome these issues, we go for simplification. One such simplification method is using Boolean algebra laws. We can use Boolean algebra laws, nothing wrong, okay, for any given expression. But people thought this particular process of using the Boolean algebra laws in simplification is a tedious process, and you may not get any idea of when I reach the final state, okay, because laws will be there. You can keep applying the laws and you can simplify the given Boolean expression. I can also call Boolean function, okay. Let me come to those things little bit later, okay. Now, once the Boolean algebra laws are a kind of tedious process, using these laws is a tedious process, as well as the second problem is you have to remember all the laws. It is very difficult for a human being to remember all the laws because we have hundreds of laws. Remembering all the hundreds of laws and applying at appropriate places or suitable places in order to simplify will definitely consumes much of the time. To overcome all these drawbacks, to overcome all these problems, the K-map is it came into existence. So Karnaugh is a mathematician, okay. Karnaugh is a mathematician. He has given this particular technique of simplification, or simplifying the Boolean expressions or Boolean algebra expressions or the terms. Karnaugh has given his own technique, that is the name Karnaugh map, okay. So let me get into Karnaugh map, okay. See, Karnaugh map it is basically used for designing a circuit we call switching circuits, okay. Then there are, as I told you before, there are two problems which exist with the previous method of using Boolean algebra laws, okay. The first one is the procedures are difficult to apply in a systematic way. The second one is it is difficult to tell when we have arrived at the final solution, or we call minimum solution, okay. So therefore K-map is one technique, and we have some more techniques which have say succeeded the K-map. One such technique is Quine-Mikulski technique, which also overcomes some of the drawbacks of K-map, because K-map is also having some drawback. But let us not get into the drawbacks of K-map now itself, because we have not yet studied K-map. Once after we study K-map, we will come to know what are the drawbacks of K-map, okay. So later we can think of the other techniques which are succeeding the K-map, okay. The K-map is useful tool for simplifying and manipulating switching functions of any number of variables. So I mean to say variables means the literals which are participating in the given function, okay. Next, how to write the K-map? This is very important, okay. So K-map is like, it is a kind of a matrix, okay, but don't tell this as a matrix, but it looks like a matrix. Then how K-maps are written, okay. So before we understand how K-maps are written, what is the code which is used to write the K map. Okay. So, let me put like this. Okay. All of you know we have the number system in digital electronics. Okay. Which are all the number systems we have in digital electronics? We have binary number system. So, all of you know that binary number system will going to take the value 0 or 1. Okay. Next, we have the decimal number system. The decimal number system is, it starts from 0 and it goes, say for example 0, 1, 2, 3, 4, any number n. Next, we have the hexadecimal number system. Okay. Hexadecimal number system is starting from 0, I get 1, 2, I say 9. Then we have the hexa numbers or hexadecimal numbers starting from capital A or small a, anything we call A, B, C, D, E and F, E and F. This is decimal number system and this is binary number system. We also have one more system called as octal number system. Octal number system means 0 to 7. If you look at these codes, okay, I have binary number system, I represent everything in zeros and ones, and I have decimal number system, it is starting from 0, 1, 2, 3, any number I can take. Then we have the hexadecimal number system starting from 0, 1, 2, 3 up to 9 and A to F, and we have octal number system 0 to 9. See, if you look at this thing, you can summarize, right? You can put it in a nutshell. Like number system, we have like binary number system which takes 0 or 1, that means I have only two values. Then we have decimal number system which take 0 to n, that means any value, 0 to n, any value. Next, we have hexadecimal number system which is starting from 0 to 9, that means 0 to 9 means I have totally 10 values. Then following that A, B, C, D, E, F, that is totally 6. So, 10 plus 6, totally I have 16 values here for the hexadecimal number system. Then I have for the octal number system 0 to 7, totally 8 values. Along with this, we also have one more number system, that is called as BCD number system. BCD means, I write it here, BCD. BCD means binary coded decimal. Binary coded decimal is also one more number system, okay, which takes the value from 0 to 9. Why? Because if you know that decimal numbers are from 0 to 9, and binary number system, binary coded decimal, that means we will going to code all these decimal numbers in binary with 4 binary values or 4 binary digits. This is called binary coded decimal. Done? Okay. These are all the different number systems which are present in digital electronics. Definitely all these number systems are called as the weighted numbers. I mean to say that every numbers which I present in any of these number system will going to get a weights. Okay. Say for example, what is weight? Okay. Let me take the decimal number system. I want to represent, say 8 is a decimal number. I want to represent 8 decimal in binary. How do we represent? Okay. I represent 8 decimal in binary as 1, 0, 0, 0. How I am representing this as 1, 0, 0? Why it is 1, 0, 0? Why not something else? Definitely this is a question which arises in your mind. Why it is 8 means we have one code called as weighted code, and that weighted code is called as 8421 code. What is 8421 code? Weight. You know that all this 1, 0, 0, 0 is a binary number. Binary means how much? 2. Binary means 2, right? I will write here. This is nothing but 2 binary numbers. Okay. Each and every binary number will going to get 2 to the power of something, the range we call, okay, power. What is 2 to the power of this? It is nothing but 2 to the power of 0. What is 2 to the power of 0? It is nothing but 1. Next, come to the next one, 2 to the power of 1 next, because we start for binary 2 power starting from 0 to any value. Now I will start with a 0, I started with a 0 and I got 2 to the power of 0, anything to the power of 0 is definitely 1, right. So I got 2 to the power of 0, that is 1, that is why the weight for this particular bit is 1. That is the reason we have written 1 here. Next weight written is 2. Why it is 2? Because 2 to the power of 1 is always 2. That is the reason it is 2. Next we have written here 4. Why it is 4? Because 2 to the power of 2. Because 0 power, 1 power, 2 power. 2 to the power of 2 is definitely 4. That is why it is written 4. Next 2 to the power of 3. Like that I can next write 2 to the power of 5, or say 2 to the power of 3 for example. 2 to the power of 3 means it is 8. 2 to the power of 4 means it is 16. Like that, this 84, we in general we call 8421 code. That 8421 code can be extended to any value towards your most significant bit, because if you look at this code, bits 100, there are two things you need to understand here. One is the least significant bit. This is the most significant bit. Most significant bit will always going to have a higher power, and least significant bit will going to have very lowest power. Lowest power in this is 2 to the power of 0, highest power in this case is 2 to the power of 3, that is called 8. So here we have got the weights 8, 4, 2, 1. If you add the weights for the bits which is having 1, binary 1, I am repeating it, you have to add the weights for the binary values which is having 1, logic 1. If you look at this one, in this case this is having logic 1 for the weight 8, then all other bits will going to have the binary value 0. That means the weight for this particular, the binary value for this particular weight is 0. The binary value for this particular weight is 0. The binary value for this particular weight is 0. That means this is nothing but 8 plus 0 plus 0 plus 0. This is nothing but 8. This is a decimal number. 8 is a decimal number. How do I represent decimal number in binary? 10000, and I represent for this the base 2. For 8 I will going to represent the base 10, because that is a decimal number. Please understand here we have decimal number starting from 0 to any value. At the same time, if you look at here, we have a hexadecimal number. In hexadecimal number starting from 0 to 9, because 0 to 9 is also called as decimal number and it is also called as hexadecimal number. But when I say hexadecimal number, the base is 16. We write 16 as the base. For octal number, the base is say 8. The maximum value is 7. 7 is the maximum value and the base is 8. And if you say BCD number will going to represent, it will be represented with the base 10. You can say that they are the BCD numbers. Then okay, after understanding these things, so let us move to K-map. Okay, how K-maps are written? Okay, so now K-map is written like a kind of a matrix. Okay, you know that we will going to have the Boolean expressions. Let me write the Boolean expression for you first. How a Boolean expression looks or Boolean function looks. Okay, so I'll take two variables, okay, a and b, and I call that is a function f of a b, a comma b. It is a function, f is a function of two variables a and b. You know that in digital electronics I have two variables, say for example a and b. When I have two variables a and b, how many binary combinations I will going to get? I will going to get number of binary combinations as 2 to the power of n variable. What is n variable here? The n is nothing but two variable. A is one variable, b is one variable. So I have two variables. When I have two variables, then I will going to get 4 combinations of ab. That means ab can have 4 different values. What are those values? Let me write for you, right? Okay, I have a and I have b. If you take a binary value 0 and 1, how we can allocate 0 and 1 to these variables a and b? I will write it. So first I can write for both the variables a and b 0 0, definitely. Next I can write variable a as 0 now, and I can write variable b as 1. This is one combination. Then I can write a is 1 now and b is 0. This is my third combination. And I can also assign both a and b as 1 1. This is my fourth combination. That means looking at this, you can easily understand that for a two variable function f of ab can give me 4 different values of ab. What are those 4 different values of ab? That is 0 0, 0 1, 1 0, 1 1. These are 4 possible values I would get from a function f of ab. Next, I want to represent this A and B, or say I want to represent 0 and 0 for this A and B. In terms of A and B, how would I represent? I want to represent this. A is 0, B is 0. How do you represent in terms of AB now? I do not want to represent in terms of 0, 0. I want to represent in terms of AB. How do I represent? I already told a normal value. Say for example, A is a normal value. The value for that one is 1. If I want to say complement value of A, that is nothing but A bar. We represent like A complement, and the value is nothing but 0. So, always we treat here A is a normal value and the binary value for that is 1, a logic 1, and we have a complement value for A, it is termed as A complement and its binary value is 0. If you follow this in writing the 0, 0 in terms of AB, then I can write A is 0 means what I treat, this is A bar. So, I will write A bar. Next, B is 0. When I say I have taken this example for a variable A, and this holds good for any variable. Okay, you can take any variable for that matter, right? So, then B is also 0, then I write it is B bar or B complement. Next, I take this one, A is 0, then if A is 0 means what I consider? I consider this as A complement. Next, B is 1. So, in this case it is B is 1. In a similar way, if you just relate A is 1 means I write A. If A is 0, I write A bar. If you apply the same rule here, you will going to get this as B. Why? Because B is equal to 1. Next, I write here A is equal to 1, that means I write A. Then I write B is equal to 0, then I write B complement. Then come to the last combination, I write A is equal to 1, B is equal to 1, then I would write this as A B, right. So, these are all 4 possible combinations I get out of A B if I represent this in binary number system or binary values. So, this is A bar B bar, A bar B, A B bar, A B. Then after knowing these things, there is one more important thing you must understand when we before going to K map. We have min term and max term. What is min term and max term? See, min terms are called as sum of product terms. We have min term and max term. See, min term and max terms are also called as, see, min term is called as sum of product term and max term is called as product of sum term. Now, if you look at this particular table that I have written here, A bar B bar, I call this is one product term. This is one product term because look at here, A bar dot B bar. Dot is nothing but a multiplication operation.